Hello, this is the review guide for regular physics and the fall semester exam. You guys have the answers for this, so I won't be solving them in entirety, but I'll kind of go through and give you guys some hints. The first one, he starts from rest, so his initial velocity is 0 meters per second, and he's accelerating for a time of 5 seconds at a rate of 3 meters per second squared. So that's his acceleration, and what we're looking for is his final velocity. And so we could use the equation VF equals VI plus a times t. And once you have that final velocity in meters per second, then the conversion from meters per second to miles per hour is that there are 1609 meters in 1 mile, and there's 3,600 seconds in 1 hour. So your seconds would cancel, your meters would cancel, you'd be left with miles per hour. So you would multiply by 3,600, divide by 1609. For number 2, he decides to slow down if he was traveling at an initial velocity of 22 meters per second, and it takes him a distance of 37 meters to slow down to a final speed of 14 meters per second. What's his decelerations? We're looking for A. The equation that would relate VI, VF, D, and A is the one probably most common forgotten. VF squared equals VI squared plus 2AD. So you can then solve that for the acceleration. And you would get a negative number because he is slowing down. For the next one, pushing the snowblower across the driveway. If he pushes for a time of 6 seconds and accelerates from rest, so you need to know that would mean his initial velocity would be 0, at a constant acceleration of 2.5 meters per second squared. If you're looking for how far, the equation that would relate d, a, vi, and t would be d equals vit plus 1/2 at squared. Then if a snowball is thrown upward with an initial speed of 18.7 meters per second, how long does it take to reach the top of its path? What you need to know is that at the top of its path, its final velocity will then be 0. And that the acceleration, once it is going through the air, is just the acceleration due to gravity, negative 9.8 meters per second squared. So if we're looking for time, we could do VF equals VI plus a times t, and we know everything except the time we could then solve for. Then here if we have an icicle, if an icicle fell from rest, so initial velocity would be 0, from the roof that is 7.5 meters tall. That means it's going to fall down a distance of 7.5 meters. So I'd make that a negative. And you want to know what's its final speed just before it hits the ground. And we know this icicle is in free fall, so the acceleration would be negative 9.8 meters per second squared. The equation that relates VF, VI, A, and D would be VF squared equals VI squared plus 2AD. When you plug this in, you will not get a negative for the VF because you're going to be taking a square root, but you should then know that this will be negative because it is downward. Moving right along to motion graphs. Number 6, the following graph is your displacement versus time graph. Anytime you see a motion graph, you should write down the key information you're supposed to be remembering. For a d versus t graph, the slope is velocity. That will be the key thing that will help me out here. So it asks, when did the snowmobiler stop to blow his drippy nose? So that means when is his velocity 0, so when is slope 0? And that would be at a time frame of 150 to 300 approximately seconds. When was the speed changing? When would he be speeding up? And so that's right here at the beginning as that slope is increasing. Notice that slope of the line is increasing. So that would be from 0 to 100 seconds. And what was the snowmobiler doing from 100 to 150 seconds? And during that time frame, it's a constant slope, so that just means he was moving at a constant forward velocity. To find the slope of the graph from 300 to 400 seconds, slope is the rise over run, or some of you may like y2 minus y1 divided by x2 minus x1. And so for 300 to 400 seconds, it's actually going to fall 400, so it's negative 400 meters. And it's going over running a time of 100 seconds. So we would get negative 4 meters per second for the velocity. And this slope tells us that he is going backwards. He's going back to where he started. Notice his displacement is going back towards the 0 mark. Sketch a V versus T and an A versus T for this ride. And so if I did my V versus T, for the first segment he was accelerating, so on a V versus T, that's a linear line. Then he moved at a constant velocity, then he moved with 0 velocity, and then he moved with a constant negative velocity. For the A versus T graph, it would be a positive acceleration for the first part, and then all of the other segments will actually be on the 0 mark, because when you are moving at a constant velocity or stopped, your acceleration is 0. This next graph, this is a velocity versus time graph, and if I wrote down my key things here, I would write down that the slope equals acceleration and that the area equals displacement. So where is he moving? Is he moving with a constant velocity? No, because his velocity is decreasing, so this won't work. Is he moving with a negative velocity? No, he's changing his velocity. Is he slowing down? Yes, his velocity is going from some value to 0. Is he changing directions? No, because he hasn't actually gone below in a negative velocity direction. Is he speeding up? No. Is he moving with positive acceleration? No. Is he moving with a constant acceleration? Yes, because he is moving with a constant slope. It is a linear line. For number 8, determine the velocity of the object as portrayed by the graph below. Here we have a D versus T graph. So again, our key information is that the slope equals velocity. So if we want to know the velocity, we would do the rise over the run. So it goes up 20 meters, and it goes over 5 seconds. So we would get 4 meters per second.